Welcome back. In this lecture we are going to talk about the key parts of electric car and their function. We will then look into how they all operate together to create one of the most advanced vehicles on the planet. In this figure you can see key parts of electric car. First, we have charging port with the connector and the cable. We have the high voltage traction battery and the low voltage auxiliary battery. We have an electric motor and transmission system which is used for propulsion. And finally, there are several power electronic converters that are used for battery charging, for driving the motors, and for regenerative braking. The schematic shows how the different components are connected to each other in the electric car. To explain what is inside the electric vehicle, let us follow the power flow direction and take a look at electric car to identify the key components. The first part we look at is the charging port with charging connector and cable. The charging port together with the connector and the cable allows electric car to connect to external power supply in order to charge the traction battery pack. The charging port is often referred to as the vehicle inlet. If the car is charged with the power from conventional electricity grid, it requires an onboard charger, which is power electronic converter. A power converter is made of high power semiconductors devices, which act as high-speed switches. Different switching states alert the input voltage and current through the use of capacitive and inductive elements. The result is an output voltage and current which has a different magnitude and waveform compared to the input. The onboard charger converts the incoming alternating current or AC power supplied via the charge port to direct current or DC power for charging the traction battery. The onboard charger is like phone charger but can handle much higher voltages and powers. Next is high voltage traction battery, which is the heart of any electric vehicle. Generally, the battery is located at the bottom of the car, but this can vary depending on the manufacturer. The role of the battery is to store energy for the propulsion of the vehicle. The battery has a battery management system that monitors and regulates the battery charging characteristics such as voltage, current, temperature, and state of charge. The energy content of the battery is normally expressed in kilowatt hours. Nowadays, electric cars have battery size in the range of 10 to 100 kilowatt hour. Let us now look at the battery technologies that have been applied to electric cars. First is the lead acid. The prospects for the use of the lead acid batteries in EVs are limited due to low energy densities, sensitivity to temperature, and life cycle. Next is nickel metal hydride batteries. They have been extensively for traction purposes and are optimized for high energy content. Finally, and the most popular, are lithium-based batteries. Lithium batteries are classified by the type of active material into lithium-ion liquid electrolyte and lithium-ion polymer electrolyte batteries. The lithium-ion type is generally preferred for EV applications, mainly driven by its high energy density. The table shows how a 20 kilowatt-hour lithium battery has much lower weight than its competitors. When we drive an electric car, the power flows from the battery to motor and to the vehicle accessories like light and audio system. To regulate the power between these devices, it is necessary to use power electronic converter. In electric car, a DC to DC converter steps up the DC voltage to traction battery pack to a higher DC voltage needed to run a motor drive. A secondary DC to DC converter, not shown in the diagram, is used to step down the voltage on the traction battery pack to charge the lower voltage auxiliary battery. The next component is the motor drive. The motor drive controls the speed, torque, and rotational direction of the motor. Depending on the motor drive is a DC to AC inverter or DC-DC converter that is used to control the power flow between the battery and the motor. Unlike power converters we have seen earlier, the motor drive is bidirectional converter, capable of delivering power to the motor for propulsion but to remove out the motor for regenerative braking. We will now look at the electric motor, which together with the batteries are the two vital parts of the electric car. The electric motor is responsible for converting electric energy to mechanical energy for driving the wheel via the transmission. Normally, a single gear transmission with differential is used as opposed to variable gear found in combustion engine vehicles. That is why electric cars are automatic gear cars by default. This is due to unique nature of electric motor to deliver close to full torque at all speeds. Further, the same electric motor can be both as motor and as generator during driving and regenerative braking, respectively. Finally, the two key parts of electric cars are the auxiliary battery and power electronic controller. The auxiliary battery provides electricity to start the car before the traction battery is engaged and also power the vehicle accessories. The auxiliary battery is usually 12 volt for current vehicle but may be increased to 48 volt for future vehicles. On the other hand, the power electronic controller directly controls the different power converters and hence indirectly the operation of battery, motor and the vehicle. It uses the driver, accelerator and brake pedals to control power flow and select operating mode between driving and regenerative braking. It controls the onboard charger and the battery charging together with the battery management system. Now that we know the different parts of EV, then let's look at how does the EV works based on the electrical power flow. This figure shows the typical electrical layout of components in the electric car as seen earlier. Let us analyze step by step. The power is delivered from the AC grid to charge the battery via the onboard AC-DC rectifier and the DC-DC battery converter. When the car is in driving mode, the power provided by the battery goes through the battery DC-DC converter to high voltage DC bus. Then the DC to AC inverter of the motor drive sends the power to the motor. The motor then converts the electrical energy to mechanical energy and it is sent to the wheel via the transmission. Further, a DC-DC unidirectional converter steps down the voltage from the high voltage DC bus to charge the auxiliary battery, which in turn powers the vehicle accessories. To wrap up, the traction battery, the electric motors and the power electronics play a key role in the operation of electric cars. Since power is exchanged between these components electrically using cables, it provides great flexibility in design of the car. This flexibility is not possible with cars with mechanical drivetrain due to large size and weight of the mechanical components.